Okay, could you all see my screen?
Yes.
Okay. 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 So today we're going to read again the late-related paper. But since I'm fairly familiar with this topic, so I could talk a little bit about what the people have been working on in the recent 2 decades, many recent 1 decade, and how it came to there. So I think this is super deep diamond business began about less than 10 years ago. So it's a Pearson EL 2014 Nature paper where they find a ring woodite. So at that time, they opened another window. So he found a ring woodite and it was characterized as a true ring woodite. Since those diamonds, they could preserve the minerals. So the ring woodite is trying to expand at the time, but diamonds is really hard, so kept it from explosion. So they characterized it by Raman. They first analyzed it by XRD. Actually, it's not the first person identified was another Graham Pearson. It was some other visitors visiting their lab, another mineralogist, and find something that's weird. And then they look carefully for some of the very small inclusions, and people realize, okay, actually it's a ring woodite. And so they also did the Raman, and then they identified it's about 2% of water, which is big shot. So it's quite interesting, and that's pretty much the first real mineral that people generally agree that's coming from the sublithosphere. So at that time, this sample is from Huina. Actually, this people pronounce it Juina, but Juina, I think. Maybe I made some mistake in my spelling, but it's found in Brazil. So, so in Portuguese, J is pronounced as H, similar in Spanish too. Okay, but anyway, it's not that important. So at that time, that when they found this super deep diamond from this Brazilian location, then people began to look more and more samples from the sublithosphere because with the majority, like more than 99.9% of diamond inclusion so far as people recognize are from the lithosphere. But the Graham Pearson opened another window saying, okay, some of the minerals could from deeper in the lithosphere. We know. Then I think at that time there were many there's 2 ways of doing that. So one way is that, okay, people still looking at this, and then some other collaborator, for example, at Nastola, at Padova University in Italy, for example. So they have gathered a lot of natural diamonds in these different sites. Another place that made a significant contribution was from the Gemological Institute of America, Gemological Institute of America, You could Google them and look at their websites. They have very beautiful pictures. So at that time, since people realized, okay, some of the mineral inclusions could come from really deep. So Gemological Institute of America, they have a huge amount of collections, including very, very big diamonds, as large as well like Hope diamonds. I don't think Hope diamonds belong to them, but the Curland diamonds were many diamonds, but as big as your fist. So those extremely large diamonds, people began to look at them, but also look at tens of thousands of collections accumulated at the Gemological Institute of America throughout the world. So each week there are some new samples. So they were working on that. Then another group, for example, particularly by Sherry et al., Steve Sherry from Carnegie Institution of Science. So they are at Washington, D.C. And the Gemological Institute of America, one of the headquarters is in New York City. The other is in San Diego, California, where I stayed actually. So Sherry, for their group, they work very closely with them. And so one postdoc called Ivan Smith, so he identified some very large diamonds through them. I think in 2016, it's another major paper where they find those huge diamonds that come from relatively deep, but also with metals, basically. Carbon inclusion as well as H2 and CH4 fluids by Raman. So these are relatively large samples. But not only that, because of these collections of samples becoming available, Graham Pierce at the University of Alberta, so for their team, they did a lot of mass specs. So it's a different kind of mass specs. They have analyzed, so they analyzed in my recollection sulfur isotopes. And as well as the, like say, for example, helium 3, helium 4 ratio that I analyzed, etc. For the different type of inclusions, then from relatively deep. Then they made a shot in the market. So this is one way to go. And since actually Graham Pearson was working with Steve Sherry as a postdoc many years ago, so that was their 1998 paper in GCA, where they first did the rhenium osmium isotope through the sulfides in diamonds. So well, that was from the continental lithosphere, but it did talk about the story of the lithosphere formation at the time. But now we are talking about the super deep diamond business started, people began to aware and in 2014 and have a lot of progress. So this crew of Carnegie Alberta group and work closely with the Gemological Institute of America. So this is sort of, let's say, one alliance. So as I sent you the several other attachments. So this Carnegie associated people, they disagree with the paper that we read today. So there's another group of people, which is Trauner, the people we're going to read. So what they're doing is slightly different. So they do have some samples, but not as good as those samples get from Gemological Institute of America. And so those samples that they got so far are many from the collections, particularly from Caltech collections. So they did get some museums. So what they did is that they went to the synchrotron beam, particularly as the APS, as well as a photon source in Chicago. So what they did is that they shine a very strong X-ray to the samples. So basically, you could consider them to use extremely strong XRD. I don't know the exact number in terms of the voltage, etc. Parameters for this beam, synchrotron beam line. So Lei probably should do it. No, she's trying to work on it. And this is much more powerful than any of the XRDs that we have in most of the labs in different institutions around the world. So for this central beam, they're able to characterize the extremely small samples, as they discuss in the Trauner paper. So it's like 2.5, 0.4 microns, for example, in terms of this kind of size of samples that could be characterized. So using this very strong synchrotron beams, people are able to characterize some small samples that could not be characterized before by the normal XRDs that people have in their own lab. So by doing so, people began to analyze more and more samples. So they find the I7, I think, I7 or I8, I forgot. So now they found the dipmolyite. So actually, there are different kinds of custom perovskite. I think there's two types. Another type, the brillite. I forgot the exact crystal structure. It looks different than the dipmolyite that we're going to talk about today. So I think this opens another window. So using the synchrotron beam at the different synchrotron beam centers around the world, we have a lot of them now. There's one in Chicago. There's one at Lawrence Berkeley. There's one in Ottawa, Canada. There's one in Shanghai, China. There's one in France and Germany, in UK, in India too. So there are more and more beam lines that are building and operating and could be able to characterize the samples. So another advantage for using the beam line is that, okay, since some of the inclusions are very small that people probably didn't recognize before, now they can recognize them. And then there is a theory behind that, at least some people think so, is that the super deep diamonds, maybe they have a lot. Maybe they just not only have those 5, 10 grains people know so far. Maybe they're way more than that. Maybe they're 50,000 grains somewhere, but they're just been hitting a lot of diamonds. So together with the inclusion from the lithosphere, for example, if this is lithosphere, this is a lithosphere grains that are relatively large, and then you have one, this one, for example, from sublithosphere. And then you're surrounded by a lot of large grains from lithospheric diamonds, inclusions. Then it's very hard to characterize those by the normal XRD. So you have to, it's much higher spatial resolution to characterize them. And there's another possibility is that people think in the super deep places, the grains are likely very small, much smaller than what we have, the grains in lithosphere. So likely the super deep diamonds are all very small. So this is some of the stories behind that. So it's interesting. We are going to read the paper Leading by Lei today, and also hopefully Lei could let us go through the corresponding comments to that. So, okay, by that I will stop sharing and I will ask Lei to share her screen and continue with the paper.
Okay, can you see my screen?
Yeah, your voice is a little bit weak. Could you speak louder?
Now it's okay?
You could go to 100, I think.
Okay, it's clear now?
It's better. Go ahead.
Okay. Today I'll lead the paper reading. The title is The Discovery of Diamond Calcium Silicate Perovskite as Mineral from the Lower Mantle. And actually, I think this paper reports the first ever natural silicate included in diamond obtained from the Earth's lower mantle. And it's the Diamond, and the Chinese name is Maogai Guishi. And when this paper published, and the Nature and Science published the other two articles simultaneously reporting the geological discovery of the important mineral diamond in the lower mantle. And the first is from the Nature News. The title is Diamond Deliveries Long Sought Mineral from the Deep Earth. And this comes from the Science Perspective, written by the Fei Yinwei. The title is Perovskite Retreat from the Lower Mantle. And those three reports about the diamond demonstrate that these minerals are very important, and it's a new mineral for us to open the window to understanding the deep earth. And before we start, I'll introduce the first author. This is Oliver Joyner, and who is a research professor from the United Nevada, Las Vegas, and he got his all education degree from the University of Cologne. And his research focused on the mineralogy, crystallography, and dynamic compression. And as I know, she focused on the high pressure physics mineral. Mainly, she always used the micro XRD to analyze some high pressure physics minerals. And that's about the first author, Oliver. And then I want to introduce the Huchrome Mall, and this is Huchrome Mall bought in the Shanghai, China, and and she is she's a scientist who made many discoveries in high pressure geochemistry and geophysics. So the Oliver named the mineral diamond after the Huchrome Mall, Dave Mall. So he named it. And then I introduce this chemical formula. Calcium silica O3. We know this formula, chemical formula, as the whole last night at the low temperature, which is a common mesomorphic mineral, and then it became the braunite at the intermediate pressure in 2018 by the Brinker. And then it became the demo. This paper mentioned at the high pressure in 2020 with a cubic structure. And this something about this chemical formula. And then I want to introduce some environment of this mineral. In the early time, some scientists, some previous scientists started the AbO3 perovskite type solid solution. Then later, some scientists synthesized the high pressure calcium silicate perovskite in the lab, and they proved that it should exist in the lower mantle. But scientists had never seen it in the natural geological samples before, because it cannot retain its structure after being removed from the high pressure environment. Like this, AbO3 perovskite can turn into the glass if it lived from the high pressure environment. But in this paper, it's the stress of the diamonds that keeps the inclusion at high pressure. Diamonds are very strong, so it can bring the inclusion from the deep earth to the surface, Earth's surface. Then why this mineral can deserve the Nature and the Science journal published the report it? I think there are two main reasons. The first is this mineral can hold many elements that are incompatible in up mantle in minerals. The second is this mineral constrains the budget and the distribution of REs and LILEs and the elements with abundant radioactive isotopes that makes an important contributions to the heat of the Earth's mantle. So I think this is the importance of this new mineral diamond. Because I mentioned above all, importance reason, the scientists identify this mineral as the lower mantle garbage gun. Then look at this paper's mentioned samples. This picture is the diamond come from the Orapa, Botswana, and this diamond hold a tiny black speck of diamonds. Now this sample collected in the Natural History Museum of Los Angeles County, and in this paper they got the two inclusions. I'll introduce it after. And I summarize the method of this article, including those three methods. The first is Xrf mapping. I think the authors use the Xrf to finding the anomalous elements other than the carbon to find the inclusion. So they're using the mapping to scan the diamond's surface. I think so. And then they find the inclusion. Then they use the micro XRD to analyze the structure of the inclusion, and using the LAICP mass to analyze the chemical composition of the inclusion. But in this part, LAICP mass, we know this part they use the bin size is 100 by 100 micron, and we can know the inclusion size as smaller than the than the bin size. So the authors identifies the minerals, identifies the inclusion minerals by the mass balance. They the composition of the individual mineral was obtained from the composition of the bulk inclusions. This is about the chemical composition analysis. Then let's take a look at one or three of these methods. The left picture shows us the Xrf mapping, and the x and y axis gives the sample coordinates in microns, and we can this red circle is they found the two calcium rich area, and we can know the size. We can know the size of the inclusions is 4 by 6 micron and 4 by 16 micron. This is smaller one. This is a bigger one. And then the supplementary materials shows both two inclusions of the diamond contains the iron and very little titanium. So the authors do the macro XRD to identify the structure of these two inclusions, and the left and the right figure is the XRD pattern. The red line is the diamond, and the other colors line is about the other elements representing other inclusions. So they got the XRD pattern of the diamond is that of the cubic perovskite, and this is some parameters. And this smaller one figure is about they use the IR to calculate the nitrogen contents of the diamonds. Actually, I want to find the IR data from the RRUFF website. Unfortunately, I didn't find the IR data of the diamond, and I think maybe not uploaded yet. This is about the mainly method of this paper we mentioned, and then I'll give you something about the high pressure physics. I remember I introduced before the Oliver focused on the high pressure physics in the nature. in the Nature, no matter he found the S7 in 2018 Science, and this paper demoed in Science. It's all high pressure phases in the nature. And this figure show us from the FAY 2021 science, and this figure show us the two pathways for obtain the high pressure phases in nature. The first we can see, the first way is through raising the mantle rocks from the deep interior, such as diamond inclusion, because diamonds are very strong, and it can protect the inclusion and bring it from the deep earth to the surface. And and the second way is the meteorites that were highly shocked because the collision of the planetary bodies. So these are two ways to get the high phases, high pressure phases in nature. Actually, then I think 3 days ago, the science journal published the comments come from the water, and the comments for this paper, and then the Oliver gave the response to the comments, and they discovered. Let me exist the slide. Okay, this paper is comment from the water. I think I summarize the main three suspicion. The first is they suspect the diamonds really come from the lower mantle, and the second compositions are they think the compositions are not current, and the last is they think this structured perovskite phases relies on XRD is not unique. So the authors gave some response about this comments. Actually, I think about the XRD patterns are not very unique. I think different people have different understanding. In this response, the Oliver explains the two shelters have the different understanding, and they think different degree represent the different mineral structure, and besides they aim to the XRD refinement give a debate, and this part I'm not very familiar about the XRD refinement, but I think it's show us the XRD pattern represents the diamond. Then about the another question about the compositions are not very current. Cause the water think the uncertainty of the elements tested by the LASP mass are very large, and in this response, the Oliver thing show us the X versus calcium ratios. they just compared these ratios. These ratios can offset the uncertainty. So if the uncertainty is okay about this test by the LAICP mass. And that's about this paper. And something I also have confused we can discuss together. Hello, can you hear me?
Yes. Okay. Okay. Does anyone have any question?
Yeah, I actually wanted to clarify. I didn't quite understand the remark about the lower mantle origin of the inclusions and the diamonds. I mean, what are their response to this question? Why they are sure about the lower mantle origin?
Okay. Yes. Actually, Oliver, Walter, they debate this reason mainly because the B center of the nitrogen is very high compared with other sublithosphere diamonds. Wait. Yeah. So they think the diamonds are come from the lithosphere, and but in this paper, the Oliver think the diamond, the core of the diamond originated in the lower mantle. And he think the Waddler think the no geological phases of transport from the low mantle to the lithosphere that can occur at the temperature low enough and over time scale short enough to prevent the nitrogen into the B center. So so they think it's need a long duration storage, but in the response, the Oliver think many previous show that the diamonds can fast comes from the low mantle to the lithosphere, and the previous study also proved that some interaction of the between different minerals can between the different minerals proved that the ratio of the diamonds can assistant very high fast. I think so. Yeah.
So okay, I add a little bit. So I think the argument that they're putting here, actually I will tell my opinion later on. So the reason that water think the high nitrogen content in diamonds could not represent lower diamonds is because, okay, most of the previous ones that people talk about have low nitrogen content in diamonds, and that comes with explanation because people analyze metal silicate nitrogen partitioning. It's okay. Like you could keep the video on. Coefficient. So people measure the iron silicate nitrogen partition coefficient, and people find that nitrogen prefers to participate in iron, and therefore, and also because Smith et al. That in 2016 Nature paper that I think Science or Nature, I forgot, Science I think. So they find some those metallic conclusions. And also the super deep diamonds. So people think, okay, there's an explanation why super deep diamonds have very low nitrogen. because when you have iron equilibrated with them, then all the nitrogen goes into the iron, and therefore you leave the rest of the mantle very nitrogen poor, and then you only crystallize diamond that are nitrogen poor. So people sort of give an explanation, prove it, with the assumption that deep diamonds, super deep places are very reduced. Petrologically speaking, it's true, but probably it's not everywhere, I think. But sorry, I should not put my comments on here. I should state what they say. So this is water's argument, and also water at all at the current they also argues is the nitrogen aggregation state. So the nitrogen has a B3 and B4 centers in diamonds. So they aggregate differently according to temperature. So actually people used to use this to calculate the residence time in the mantle. But nowadays people no longer use that because it's not that accurate. Anyway, so the idea is that as the temperature becomes different, the aggregation state of nitrogen in diamonds will become different. And this kind of nitrogen aggregation state could be analyzed by FTIR, fluorescence transform, infrared rate. So people use this as evidence. So water say, okay, if this is from deep, you should have very low temperature, and they're going to re-equilibrate. So Oliver doesn't agree with that, and they think that okay, some low places that could low temperature places like sublet slab, that's very likely a lot of super big diamonds coming from, and they could survive. And I think if I'm going to argue, I'm also going to hear if I'm going to write the response to the comments, I'm also going to say, okay, you're also assuming a very reduced condition that nitrogen all partition into the iron, so that indeed the diamond nitrogen poor. But if it is on sublattice slabs in relative oxidized conditions in a deep mantle, it doesn't have to be like that. So at least locally, but those are the places that a lot of super diamonds form. So from my comments, the nitrogen itself is not, I don't think it's a unique punchline to say, okay, this diamond is from deep or not. Because I think they sort of like both of them didn't, let's say, the key part actually is still the crystal structure. Because we need to find minerals that have a super deep crystal structure. That's why Pearson 2014, when they find the ringwoodite, that was a big shot, because ringwoodite is confirmed, okay, this comes from super deep. While for the rest of the minerals, sort of the people are still fighting with each other to say that how accurate the XRDs are. And if there are some controversy about that, then people infer some second order evidence. I think nitrogen content in diamonds as well, nitrogen aggregation is a second order or second degree evidence rather than the first degree. Okay,
I also wanted to ask about the other inclusions. Did they analyze anything else? Like, did they have any evidence of having a high pressure conditions maybe via these inclusions? I mean, maybe those calcium silicate inclusions are not the only ones they analyzed or not.
As for I say, I didn't know details. Like probably explain, but my guess is that of course they look for a lot of minerals, and that's if they're going to find the first one is the one they found, then people are going to publish science paper every day. Obviously it's not. So they gather a lot of diamonds, and then they scan them, and then they find some suspicious ones, and then they bring them to the synchrotron beam. So do remember, synchrotron beam is still a very limited resource. So every day, people may scan for a couple of locations in a diamond. So normally it's 1 to 3 diamonds a day. So you really bring to synchrotron beam to look at it. And normally you have a couple of days of beam time, and you only go to beam time a couple of times a year. So in the end, you don't scan many diamonds. Of course, people are trying to find as many different spectral, XRD spectral as possible at the time when spent on synchrotron beam. So but I don't know how, let's say, in this case study, any other evidence that we found. So when we wrote something down, and ilmenite, iron, and I7 in the same diamond have remnant pressure. Yeah, there's some other evidence they provide, I think, Natasha. I hope that could answer some of your questions or confusions. Yeah, another thing I forgot to say is that there's a remnant pressure now that people could measure. Basically, that comes from the elasticity of different minerals, because for those super deep, not only super deep, but for all diamond inclusion, we could say that when those diamonds formed and those minerals grow at the same time, the diamonds, okay, they are the pressure, so the inclusion didn't squeeze the diamonds much because they both have the same pressure. For example, 20 GPa, 30 GPa, whatever. And then when these diamonds up well in the shallow part, both diamond and the inclusions are going to expand because the pressure decreases. However, diamond has a very compact crystal structure, and diamond doesn't expand much. It maybe expand a little bit, but not too much. But for the rest of the silicon minerals, they're going to expand a lot. But diamond doesn't want them to expand. So in order for these minerals to keep the same size, volume, then there is a pressure between this diamond inclusions and the diamond. And those pressures is related to elasticity of the minerals. And the people also use that to sort of infer that how deep could those samples that are coming from, because because if the samples are coming from very, very shallow, maybe 3 GPa, you won't measure some remnant pressure so large because the minerals won't like decompose much. So I think this is another, like say, this to me is also second order or second degree evidence to say that the samples are coming from the deep. But there's some useful information.
Yeah, I understand. I was wondering about the other inclusions because I was hoping that maybe they had other, let's say, evidences that the association they're seeing in this central part of the diamond is really the lower mantle one. But yeah, there are no strong evidence as far as I see.
Yeah, maybe Lei, could you share your screen and show us some of the diamonds that you are about to working on now, so that people could see what the daily business looks like. It's a very dirty business. Is that most of the time you get nothing, and occasionally get something, and then you write a paper, high shot paper, high impact paper. But in the end, people are going to blame them for finding very little evidence. But Lei could show us the real diamonds that she has now. So could you share your screen, Lei? Yeah, maybe you can give a detour to explain these diamonds. People
Okay,
might not believe you they are diamonds because they don't look like diamonds.
Yeah. Okay, these are diamonds we collect from the Mengyi, Shandong province of China, and those are 10 diamonds, natural diamonds, and not the same size. We can see the diamonds are very dirty in the surface, and you can see most of them are dirty, and we can see the inclusion about the diamonds, and only okay. This one is pretty good, and we can see something, maybe something inclusion in the microscope, but other one are nearly very dirty and have some reflection of the from the surface. and we can't distinguish which there are or not inclusion minerals in the diamond. Yeah, so it's very difficult to test and found the inclusion of the diamond. Yes.
So Natasha, I think you worked on kimberlite before. Have you touched on any diamonds before?
No, I've only worked with mantle or core associations and never had to deal with diamonds.
Okay, maybe you could go to some of the one of your diamond, maybe the very first one of a diamond picture I showed earlier on. I could make a little comment. Maybe not one, maybe the second one. Third one, I think there's one looks like some fiber structure. On this one. Actually, I cannot tell. Maybe it's still the first one. I don't know. I think there's one I used to see with some fibrous structure. Because in this paper, in the comment that Water et al. They gave, they're trying to say, okay, they have a figure behind it. They say, okay, what they are seeing are not super deep diamonds, but some fibrous diamonds, because Navin, etc., because it's the same samples in Navin and several accounts. They are from University of Jerusalem, Israel, and those people, they have been working on those fibrous diamonds, those ones that people suspect those diamonds not coming from the deep, but coming from during the crystallization of eruption of kimberlite. So some of the diamonds will form in that process. And also they could be formed by some by fluids, and let's say not in a typical environment we are thinking about crystallizing those big crystal diamonds. So those could be very weird and conditions that could also lead to something similar to this, at least a current argument by Water et al. So okay. So Yang asked a question about the chemical formula. So yeah, my understanding is that, okay, calcium perovskite is the ideal case. So, but people are always talking about the possibility of some large cations like potassium, sodium. So these ones are possible because if you look at other lower mantle minerals like bitumenite, I would like to make an analogy. So if you look at the lower mantle bitumenite, you can think about the upper mantle olivine. So it doesn't host too many potassium or sodium. But if you look at a calcium perovskite like this one, if malleite, a bryite, you can consider them as a pyroxene. So it's not exactly the same, but you could think about an analogy to that. So for some of the aluminum, sodium, potassium, they could all go there, which makes their stoichiometry very messy. And yeah, so I think another thing that as far as what they are trying to say is that this stoichiometry is not perfect. Also they are trying to argue that by mass balance to calculate it, I didn't read as details of that. That they're trying to the charge balance, I mean, by Troutner response that they're trying to say. But I don't know. Because it's interesting because no one has really got a real one, calcium perovskite from the deep. I mean, this probably one of the first ones we have got. So people have no idea how it really looks like, and it's very rare samples too. And what the people synthesize in a laboratory, even though people could synthesize different compositions, those are just synthesized ones. You don't know what the composition real ones looks like. But it's interesting because, yeah, it could also be a pyroxene. Yeah. So, like, maybe you could ask Liang's question.
Yeah, I think this is a good question about the XRD pattern, and the water also debate this part. They think they think the water they think the structure the XRD pattern and have a lot of noise and could didn't identified as the diameter, and cause I I I know a little about the XRD refinement. So in the response, the author, the Oliver gives some response, some refinement of XRD about the diamond, but I'm not very familiar about this part. I think it's related to the XRD refinement a lot. Yes.
Maybe that is why they tried to do the ICP-MS as well to see if the other inclusion signals are there. So I guess that is why they used it.
So, Wumi, do you think those diamonds has a lot of trace elements?
Diamond shouldn't have much amount of trace element, but as we can see in the signal, only in the ICP-MS signal, only 2 peaks are visible clearly. So normally if inclusion is big or it's like the signal we get, they are a little flat. Like here we can see very sharp signals that are like in the image figure 2. So the signals are very sharp. So the background is actually pretty low, as we can see. So in the diamond itself, the signal of the trace element is low and we can only see sharp 2 peaks. So that indicates that those are signals of inclusion only. If the inclusions are big, generally the peaks are more rounded and spread.
So are they really compare? So Ben, what do you mean? Compare it with the synthesized one? Maybe you could clarify what your question. Oh, really? Are it?
No. Maybe, but in this paper, the author didn't mention it, and I text the previous paper about the synthetic diamond, and they didn't publish the XRD data and other information about the XR about the diamond. Then I check the RRUFF website to find some XRD or the IR or the Raman data. I didn't find anything about it. Yeah.
Okay, I think it's a fruitful discussion today. And thanks, Lei, for leading the discussion, and thanks everyone for your participation. And on Wednesday, we're going to see the speaker give a talk. Actually, I have not asked whether the speaker could record it or not. But anyway, yeah, it's great. And see you all online. Bye-bye.